Dear students, Assalamu alaikum. So today we are going to discuss about the second order phase transition. In previous lecture, we discussed about the first order phase transition, and we know that the first order phase transition is one which shows a discontinuity in one or more of the first derivatives of the thermodynamic potential. So whereas in the case of second order phase transition, uh, in this case, all the first derivatives of the thermodynamic potential they are continuous at the transition. So we call this type of transition as a continuous or second order phase transition. So the examples of such phase transitions include a ferromagnetism to paramagnetic transition or conducting to a superconducting transition. But the important point to note here is that in second order phase transition, there is no latent heat involved. So, if we plot different parameters such as the Gibbs free energy, entropy, and volume as a function of temperature, we will get curves like this. So, if we talk about the variation of Gibbs free energy as a function of temperature in case of the second order phase transition, we will see that it almost shows the similar behavior which is observed in case of the first order phase transition. That is, the Gibbs free energy is continuous in both cases. However, there are slight changes uh, uh, that the slopes of the first and second order phase transitions will be different for the case of Gibbs free energy. So what we can note here is that as we increase the temperature T, the Gibbs free energy decreases. And as we discussed, that this trend is same as that of the first order phase transition, uh, but the slopes are different. Uh, we know that the Gibbs free energy is given by H minus Ts, and whenever we increase the temperature of the system, the enthalpy of the system increases. But we know that along with entropy, along with enthalpy, the entropy of the system increases much more rapidly. So it means that this term will increases more rapidly compared to that of the increase in enthalpy. So you will observe an overall decrease in the Gibbs free energy. And also, this is the behavior of entropy as a function of temperature, because we know that dG is equals to minus S dt plus VdP. So the entropy is given by minus partial G by partial T at constant pressure. So if as we increase the temperature, the entropy increases, and the curve is continuous at the phase transition. So the difference in this case is that there is no discontinuity in the phase at the phase transition temperature, and this is because we are not supplying any latent heat in this case. So thus, as we increase the temperature, the disorder will increase. So it will result in an increase in the entropy of the system. Whereas this last one is the variation of volume, which is given by partial p by partial g by partial p at constant t as a function of temperature. So as we are going to increase, as we are increasing the temperature, we see that the volume of the system is increasing, and this can be understood because with the increase in temperature, the molecules will go further apart, so which will result in increase in volume of the system. So the difference in first order and second order phase transition is that in case of entropy and volume, there is a discontinuity present in the at the phase transition, whereas in case of second order phase transition, there is that both entropy and volume are continuous, and the reason for the discontinuities was that uh, there was a latent heat which was involved in case of first transition, that which was supplied to change the phase of the system in case of the first order phase transition. So that's all for the case of second order phase transition. So now let's move to discuss some models about the phase transitions, and the most important model that we are going to discuss today is the Ising model. So this is the simplest model uh, which can exhibit a phase transition, and it was given by Ising in 1925. So this model is about uh, the magnetic materials. So if we talk about the magnetic material, we know that iron is a very good magnetic material which shows a ferromagnetic behavior below some critical temperature, which is the transition temperature, and it can even show the magnetic behavior even in the absence of magnetic field. So the magnet, and we know the source of magnetism in case of magnetic materials. The source of magnetism is due to the permanent magnetic dipoles, which are aligned, leading to a net magnetization. So this alignment corresponds to a partial ordering of the system. So when the temperature is raised, the dipoles start to become randomly oriented, and the magnetization decreases. And above the transition temperature, the magnetization disappears and the system changes from a ferromagnetic state to a paramagnetic state. And if we talk about the origin of magnetism in any compound, the origin of magnetism lies in uh, the orbital angular momentum and spin angular momentum. So whenever there is an orbital angular momentum and spin angular momentum, there will be a magnetism, a magnetic moment which is associated with that atom. And any compound, any atom which has partially filled orbitals, it will have a net orbital and spin angular momenta. So we can say that whenever an atom has partially filled orbitals, it will lead to or a net spin angular momentum and orbital angular momentum, and these orbital and spin angular momentum will give rise to magnetic moment. And the magnetization is basically defined as the magnetic moment per unit volume. So this was all about the magnetism, the origin of magnetism. So basically, this model uh, predicts the phase transition in case of magnetic materials. So there are different types of Ising model. That this Ising model was first given for the one-dimensional array of atoms, and then it was given for this two and three-dimensional array of atoms. But we can only solve uh, the one-dimensional method model exactly. Or we can also solve the two-dimensional method model as well, but in the absence of magnetic field. The other cases can be dealt by using some kind of approximations and computer simulations. So let's discuss this Ising model. So the Ising model, in this Ising model, we consider an array of lattice side with the nearest neighbor interactions that depends on the manner of occupation of the neighboring sides. Okay. What this model basically tells us that it only considers the nearest neighbor interaction, which depends only on the manner of occupation of the neighboring site. What we meant by the a manner of occupation is that so this is these are some atoms which are placed on the lattice sites, and these atoms have a permanent magnetic moment, which is shown by this arrow, which corresponds to spin angular momentum. So it's basically a magnetic moment. So this magnetic moment can either point upward direction, or it can either point in the downward direction. So the manner of occupation means that if we consider the interaction between these two up spins, this interaction will be different from the interaction between up and down spins. So the energy of interaction between the neighboring spins will depend on the manner of occupation of the neighboring sides. That how these spins are arranged on the neighboring side. That whether they are parallel to each other or they are anti-parallel to each other. So to study the statistical mechanics in the Ising model, as we discussed that in this case, the phase transition essentially result from the interaction energy among atoms, and we include only the nearest neighbor interactions in case of the Ising model. To study the properties, so we can also study properties like magnetic susceptibility by using the Ising model. But for that, we have to apply an external magnetic field, and then we have to see the response of any material to the applied external magnetic field. And so whenever there is an applied magnetic field, it will provide an additional potential energy, which is given by minus mu b sigma I. So you can also write spin as, you can also denote spin as sigma I or si. So you can also write si here as well. In Bowley, he's following the notation sigma I, but I will prefer to write denote spins with SI. So whenever we apply a magnetic field, we have this additional potential energy term in the energy, which is noted by minus mu b SI. So where mu is the magnetic dipole moment, which is given by this formula, which is equal to minus, which is equal to g mu b j. And from quantum mechanics, we know that the magnitude of j is basically given by j into j plus 1 square root. And this mu b is known as the Bohr magneton, which has a fixed value of 9.274 into 10 to the minus 24 ampere meter square, or joule per Tesla. And this G is known as the Landau G factor, uh, which for electrons has a value of 2. So this is some constant number. This is also a constant number. So SI, it basically denotes the spin value, which is assigned to each value. So as we see that the spins can either occupy a site with upspin, or it can occupy a site with downspin. So if I say that a spin is occupied with upspin, then the value of SI will be equal to plus 1. And if it is down, then it will be given a value of minus 1. So let's consider a configuration that you have a lattice, different lattice sides on which different spins are arranged, and you have also applied an external magnetic field. So we are going to write the Hamiltonian of such a system. So since we are going to write the Hamiltonian of the system, so we can think that there are two kinds of energies that will be involved in the Hamiltonian. The first one is this interaction energy between the neighboring spins, since we are only considering the interaction of the neighbors, and plus there will be a potential energy term which will come into the picture whenever there is an applied magnetic field. So the total Hamiltonian of this of such a system will be equal to minus j into summation of ij, which is the interaction between the nearest neighbors, sum over nearest neighbors, up to n, depending upon how many spins you have, and the product of si into sj. And this interaction, that is the interaction of the type minus js1 s2, basically this interaction is known as the exchange interaction between spins. And the interaction energy due to the applied magnetic field, that is the interaction of magnetic moment with the applied magnetic field, is given by minus mu dot b. So it will have a value of minus mu b summation of I si, that it since as you are summing over all the spins that are present on the lattice. So here we can note that the sum is over SISJ, um, uh, and is for the nearest neighbor only, as we also discussed previously, that we will only consider the nearest neighbor interaction, and we cannot uh, we have to uh, take only we have to take only the nearest neighbor interaction, and only we have to count it once. That if there is a spin s1 on one side and s2 on the other side, you have to consider only this interaction once, that the interaction of s1 with s2 or s2 with s1. So the double counting should be avoided here. And also, as we discussed earlier, this si will have a value of plus minus 1 here, depending upon that whether the spin is up or it is down, and j is some exchange constant, or it is known as the exchange energy of the system. So this is basically has a unit of energy, whereas the product si sj will always be a number. So this is the Hamiltonian of a system based on the Ising model, which have two terms. The first term is the interaction energy term, which is known as the exchange interaction term, and the second is the energy which is present whenever there is an applied magnetic field to the system. So, how we can find this Hamiltonian of the system? It is very easy to find the Hamiltonian of the system depending upon that how many atoms we are considering in the system. Suppose so. Let's see that how we can write this first term for the case of three spins s1 and s2 and s3, which are arranged on some lattice site. So let's consider that there are three spins, um, S1, S2, and S3. So since we are only going to consider the interaction of nearest neighbor, so we will consider the interaction of S1 with S2 and S2 with S3. So this first term, this summation, in this case, when n is equal to 3, will be written as S1, S2 plus S2, S3, whereas this S1 and S2 and S2 and S3 will have a value which will depend on the manner of occupation of these spins, that how these spins are arranged on the lattice. If S1 is up and S2 is up, we know that S1 and S2 both have a value of plus 1, so this product will give you plus 1. And if the manner of occupation is such that the spin 1 is have a spin down and the spin 2 has a up spin, then this product will give you a value of minus 1. So in this case, you will have a plus 1 here, and in this case you will have a minus 1 here. So this product will depend on the manner of occupation of these spins. So for this case, if there are only three spins, then you can write this summation as minus j, sorry, minus j s1 s2 plus s2 s3. And similarly, if you have four spins, then you have to add another term as well. And whenever there is no applied external magnetic field, then this term will be zero. But whenever there is a magnetic field applied, then you have to consider the interaction of each spins with the external magnetic field, and then you have to add in this Hamiltonian of to find this Hamiltonian of the system. So I'm not going into the details of the Ising model for the case of second order a two-dimensional Ising model and three-dimensional Ising model, because it is we don't have enough time to cover all these three cases. But Ising model is a very important model, so at least you should have some basic understanding about the Ising model. So Ising model basically it considers the interaction only among the nearest neighbors, and this interaction is of the form or which is given here. And whenever there is an applied magnetic field, you have to add this term as well. So we can find the thermodynamic properties of such systems as well. You know that whenever if we are able to find Z and the partition function, we can find out all the thermodynamic properties of the system. And in Z, we know that there is a term which is the energy. So energy is involved. So if you are able to find out the energy of the system, it means that you will be able to find Z, and from Z you can find the rest of the thermodynamic properties of the system. So it is not difficult to understand the Ising model, and you will see that it is very easy to solve Ising model, especially in the case of one dimension for different problems. So I will do 2 to 3 problems in next lecture, and you will by which you will understand that how we can solve problems related to the Ising model. So that's it for today's lecture. Thank you.